Hello everyone, welcome to this episode of the Zoology Podcast. So, first off I want to start with an apology. I've recently become a lecturer at a university and therefore my time is being taken up with making lectures for students. So therefore, while I'm still going to be trying to put out at least one podcast a month, the overall length of each podcast may be reduced a bit. But they should still be interesting. So, anyway, let's get on with the episode. Natural selection is a key process in how a species evolves over time. But many people do not understand just how simple this law of nature is, yet how elegantly it can facilitate change. At the base of natural selection, like most things, is maths. In principle, populations have the capacity to increase in number exponentially. If one animal produces 2 offspring, and then each offspring once adult produces 2 more offspring of their own each time, and so on and so on and so on, then the total number of that species population grows at an increasingly exponential rate. Now this doesn't sound like much, but it really can be difficult to fathom for human minds, as we have not evolved to think in numbers at such a large scale. Take this for example of what I mean. Let's start with a single bacterium which divides in 2 every 30 minutes, where it would take less than a week for the descendants of this one bacterium to exceed the total mass of the Earth. Okay, now that's kind of crazy. But what about something bigger? Let's say an elephant. Well, Darwin calculated that it would take only a single breeding pair of elephants 750 years to have around 19 million descendants. Clearly though, the world is not overrun with bacteria, or elephants. But why not? Well, putting it simply, exponential population expansion is limited by the circumstances of nature. Most offspring that are produced do not survive to produce offspring of their own. In fact, most population sizes tend to remain relatively stable over the long term. This means that on average, each animal produces only 2 offspring that go on to reproduce successfully. Many youngsters will be eaten by predators, others will starve due to a lack of food, some will die to stochastic happenings, and yet still others will succumb to disease. Darwin realised this massive discrepancy between the number of offspring produced and the number that can be sustained by available resources creates a struggle for existence, in which only a tiny fraction of individuals will survive to reproduce. He noted, this can be conceived as a struggle not only against organisms including the same species, but also in a more abstract sense, between organisms and their physical environments. So, why are some organisms surviving and reproducing while other members of their species are not? Well, even when an animal produces many offspring, which are all genetically related, even if many of these happen to be twins, there will still be genetic and environmental factors that make each individual unique, and therefore they all have variation. It is this variation among individuals that is a fundamental requirement for evolutionary change to occur. While Darwin understood that overpopulation of a species in an environment with limited resources will create a struggle for existence, where some individuals will succeed, yet most will not, he also recognized that organisms in populations differ from one another in terms of inheritable traits. Darwin's brilliant insight was to combine these 2 factors, thus realizing that the success in the struggle for existence was not determined by mere chance, but instead by the biases of nature acting upon the inheritable differences that exist in all life. Specifically, he noted that some individuals happen to possess traits that make them slightly better suited to a particular environment, meaning that they are more likely to survive than individuals with less well-suited traits. As a result, organisms with these traits will on average leave more offspring than their competitors. New genetic variants occur randomly in a population due to peculiarities of genetic exchange or genetic code not being copied accurately, leading to mutation. However, the probability that particular genes will be passed on to the next generation is absolutely not random if it impacts the survival and reproductive capabilities of that organism. Over a long enough time period, depending on the reproduction rate of the organism, these non-random sorting of genes from parent to offspring result in adaptive traits in the surviving members of the species. For example, giraffes have evolved long necks which have enabled them to feed on leaves that their competitors cannot reach, giving these giraffes a competitive advantage. Thanks to this better food source, those giraffes which had longer necks were able to survive and reproduce, and so they could pass on this characteristic to the succeeding generation. Any giraffe with shorter necks had less access to food and therefore would be less likely to survive and pass on their genes. Now, because of this process, giraffes have become adapted to exploiting this new niche of a high food source. The term adaptation derives from the Latin word ad and aptus, literally meaning towards fit. as this implies the process by which populations of organisms evolve, resulting them becoming better suited to the environment of their recent ancestors. Or putting it simply, they become a better fit for surviving in that environment. This is what is known as survival of the fittest. It is not the most physically fit animal that survives, but those animals which are adapted to their surroundings the best. For example, during the Industrial Revolution, the peppered moth, which was mostly white with black spots, started to stand out in their environment, as the trees and buildings became covered with dark soot. In other words, as their environment changed, these peppered moths became less fit in the new environment, because they stood out on the black backgrounds of the trees and buildings. This allowed birds to easily spot them and then eat them. But those peppered moths which had a mutation for melanism were mostly black, and therefore they were better suited to fit into the new environment, and so their fitness could be said to have increased, as they were more likely to not be spotted by predators, and therefore had a greater chance to reproduce. On first pass, it may be difficult to see how natural selection can ever lead to the evolution of a new characteristic, if its primary effect is merely to eliminate unfit traits. Actually, natural selection as a process is incapable of producing new traits. In fact, most forms of natural selection deplete genetic variation within a population, as deleterious genes are removed. How then can an eliminated process like natural selection ever result in new, extraordinary outcomes? Well, evolution by natural selection is a two-step process. The first step involves generations of new genetic variants by mutation and recombination, as we touched upon earlier, while the second step determines randomly generated genetic variants will persist into the next generation. Most new mutations are neutral with respect to their survival value and ability to affect reproduction, therefore they are irrelevant in the terms of natural selection. However, the majority of mutations that do have an impact on survival rate and reproduction output will do so negatively, and as such they will be less likely than existing variants to be passed on to the next generation, being selected out of the gene pool. However, a very small percentage of new mutations will turn out to have some beneficial effect in a particular environment, and this contributes to an elevated rate of reproductive success. Even a very slight advantage in reproductive success will increase its prevalence in a population over time. You have to grasp this fact if you are to understand just how powerful a force natural selection can be in facilitating change over time. Natural selection itself is the central component of modern evolution theory, which in turn is the undercurrent of all biology. Without a grasp on this process and its consequences, it is simply impossible to understand, even in the most basic terms, how and why life has become so extraordinarily diverse.